In Chapter 9, we are going to talk about alcohols, ethers, and related compounds. And those related compounds are things like epoxides and sulfides. Now, when we go through and we talk about alcohols, alcohols have the functional group OH, which is shown here. One of the most common alcohols that we run into is ethanol. And for example, ethanol can be obtained from things like amylose in corn to end up with, for example, gasohol or E85 ethanol, which is used in gasoline. We're also going to talk about the ether functional group, which is shown right here, where you have an oxygen with 2 carbon groups on either side. Diethyl ether, which is CH3, CH2, O, CH2, CH3, was one of the first general anesthetics used in surgery in the 19th century. It was replaced by sevoflurane, which is shown here, which is less flammable and causes less patient discomfort. And so this is a common general anesthetic used. Now, we're also going to talk about epoxides, particularly in this screencast. Epoxides are ethers that are in rings here. And so you can see this is an example of an epoxide. Now, let's talk a little bit more about alcohols. When we talk about alcohols, as I mentioned, contain this OH functional group, which is a lot of times called a hydroxy group. It's important to remember that that particular carbon shown here is sp3 hybridized. Now, they're classified according to the number of alkyl groups attached to the carbon bearing the OH. So these are classified based on the number of alkyl groups attached to the carbon with the OH. So when we look at this, and we, for example, have a secondary alcohol, when we look at the carbon right there, it's attached to 2 alkyl groups. Here's a tertiary alcohol. This carbon's attached to 1, 2, 3 alkyl groups. Here's a primary alcohol where that carbon is attached to 1 alkyl group. This is an example of cortisol, which is an anti-inflammatory steroid. Now, a few other things. Compounds having hydroxy groups on sp2 hybridized carbons, which are called enols and phenols, undergo different reactions than alcohols. So these here, right, undergo different reactions than alcohols. So we will talk about those compounds separately, but I wanted you to be able to recognize those in case you were like, well, what about if you have an sp2 hybridized? They just go through a different set of reactions. Now, let's talk about ethers for a moment. Ethers have 2 alkyl groups, shown here and here, bonded to an oxygen. And you can have 2 different types of ethers. You can have a symmetrical ether, where there are identical R groups on either side. And then you can have an unsymmetrical ether. Sometimes this is referred to as a non-symmetrical ether. So just know that those are interchangeable, where you have a CH3 group here and an ethyl group here with 2 carbons. And you can see that these are different groups. So unsymmetrical or non-symmetrical ethers have different groups on either side, and then symmetrical ethers have the exact same group on either side. And we name those differently, so it's helpful to be able to recognize them. Now, the other thing we're going to talk about in this screencast are epoxides. These are ethers that have an oxygen atom in a 3-membered ring. These are also known as, or also called, oxirans, right? So that's just a synonym for epoxides. And so you see here, epoxide or oxiran. Now, when we talk about these, that's a really strained ring. And what we see here is the the carbon-oxygen-carbon bond angle here is 60 degrees. And that is a considerable deviation from the tetrahedral bond angle, that's 109.5 degrees. That means that epoxides have a lot of angle strain, which makes them more reactive than other ethers. Right? So let's talk about oxygen for just a moment. When we talk about the oxygen atom in alcohols, ethers, and epoxides, right, that is sp3 hybridized. Okay, now alcohols and ethers have a bent shape, like H2O does, right? So when we talk about H2O, that oxygen in H2O has a bent shape, and that's what we see with alcohols and ethers as well. Now, there's a difference here. The bond angle around an alcohol, right, is similar to a tetrahedral bond angle of 109.5, but it's a little different. So, for example, in this molecule, it's 109, and this one, it's 111. Because the oxygen atom is much more electronegative than carbon or hydrogen, the carbon-oxygen and the OH bonds, right? So this would be a carbon-oxygen, that's carbon-oxygen-OH. Those are both polar, okay, because of that electronegativity difference. Now, let's name alcohols. So, for example, let's do this example. We're going to give the IUPAC name for the following alcohol. We follow many of the same steps as when we named alkenes and alkyl halides. You need to find the longest carbon chain containing the carbon bonded to an OH group, right? So when we look at this for this particular molecule, that's the longest carbon chain, and we count 1, 2, 3, 4, 5, 6. So there are 6 carbons there. So we know with 6 carbons, if that was an alkane, it would be called hexane. And so what we're going to do here to differentiate it from a hexane is to change the E ending in the parent hydrocarbon chain to OL. And so because there's an alcohol here, this now becomes hexane nol, right? Where we've taken away the E and we've added the OL there. Then the next thing we need to do is we need to number the carbon chain to give the alcohol the lowest number. The reason we give the alcohol the lowest number here is because it is the functional group. When we do this, after we do this, we'll follow all the other rules of nomenclature. So let's go through and name to give the alcohol the lowest number, or number 1, 2, 3, 4, 5. We don't have to count anymore. If we count from this direction, it's 1, 2, 3, 4, and 3 is lower than 4. So where do we put the number indicating the alcohol? Well, it's going to go in between the hexane and the OL. So this is 5-methyl hexane 3-all, and that's written as all one word. Okay, and so this right here just tells us the location of the alcohol. There is another kind of older nomenclature that you'll see sometimes. It's not in your book, but it'll show up like this: 3,5-methyl, right? 3-hexanol. Where when the 3 is here, it indicates the position. You need to use this particularly in your homework, right? And be able to recognize either of these interchangeably, kind of like synonyms, because some chemists still use this type of nomenclature because that's how we were taught. But this is really being used more and more frequently now. So maybe the burning question in your heart is, how do we name alcohols on rings? And those have a little bit different kind of rule, which is interesting. So let's talk about alcohols on rings for a second. Okay, so let's look at this example. Okay, when we look at this example, we name the molecule and we are gonna name it, right, as cyclohexanol. Okay, and with a ring, you put the functional group at 1. So the functional group is at the 1 position. Then you need to number so that the next substituent has the lowest number. So, for example, 1, 2, 3, 4, 5. That's how we would number that. So then we would end up naming this molecule, right, as 2, 5, 5 trimethyl cyclohexanol. Okay, notice the big thing here is that there's no number because it's understood the alcohol is in the number 1 position. Okay, and so that's something that we need to kind of keep in mind, a big difference between naming a longest carbon chain and naming a ring. So a ring, we don't include the number for the alcohol if there is just 1. If there's 2, then we need to use prefixes. And we're going to talk about those prefixes in just a second. So before we talk about those kind of prefixes, I also want to briefly talk about common names. Common names are used a lot of times. You're really simple alcohols. And so a really good example here is isopropyl alcohol, which you can buy at the grocery store. It's like rubbing alcohol. And basically the way that these are named is you name all of the carbon atoms in the single alkyl group, and then you just put alcohol on the end of it. So another one, for example, CH3, CH2OH. We would, when we look at this, look there and say, hey, look, that's an ethyl group. That would be ethyl alcohol, right? So that would be how we would name it using a common name. If we were to name isopropyl alcohol using IUPAC nomenclature, we would say, okay, hey, look, that's propanol, right? We have 1, 2, 3 here. And so we would say, okay, that then is going to be propane 2 all, like this. Now, I want to show you something here with IUPAC in this naming. IUPAC just calls this ethanol because it's understood that if the alcohol group here is attached to the first carbon or the second carbon, it's the same molecule. So because there's only one real place the alcohol can be attached, we don't use a number. Same thing with methyl alcohol or methanol. There's only one place that number can be, and so we don't say where it is. We just say, hey, look, this is methanol, and then the common name is methyl alcohol. But beyond the methyl and the ethyl, we then begin to use those numbers. So that's a little bit of an exception that we see. So I just wanted you to be aware of that and didn't want you to be thrown off. Now, what do we do if we have two alcohols? Well, then we need to also tell the location of both those alcohols. So for example, this would be, the common name here is ethylene glycol. This is a lot of times used as antifreeze. And the IUPAC name is ethane 1,2-diol. So I want you to notice here, right, when we have these numbers, then we use the full alkane name. And then we also use the diol here. Now maybe the question is, well, why? Why don't we, when we look up here, right, at propane 2-all, why don't we keep the E here? And the reason is they didn't want two vowels to be together. And so we drop the E here. But if you have 2 or 3 alcohols where you put in these di and tri prefixes, then you leave the E in, okay? I want us to do an example of a ring because rings are kind of interesting. Because remember, if we just had one alcohol group, we didn't tell the position of the alcohol. But if we look at this guy, right, and when we have two alcohol groups, so with 2 or more alcohol groups on a ring, right, you number all alcohol groups. So if you just have one alcohol group, you don't number it. It's understood to be at 1. But if you have more than one, you have to show the numbers where they all are. So for example, this would be like 1, 2. So we would name this as, right, cyclopentane with an E, 1, 2 diol. And we, of course, are using that E again because we have the di here. So there are some kind of strange nuances here when we name alcohols. You'll want to make sure you review those and, of course, spell those correctly. But again, just kind of some strange small things that we have to keep up with. Let's talk about naming ethers. Now, ethers are normally assigned common names. So, for example, right? If we have an ether like here, we would name both alkyl groups bonded to the oxygen and arrange those alphabetically and then add the word ether. If it's symmetrical, we just name the alkyl group and add the prefix di, right? So for example, this has two ethyl groups here. It is symmetrical, so we would name this as diethyl ether, right? When we look at a group, an ether that is not symmetric, so let's look at this. This particular group here, there's 1, 2, 3, 4 carbons, and it's attached at that second carbon. So remember, that is called a sec-butyl group. And then, of course, the other one is methyl. And so we alphabetized based on the B of the butyl, right, before the M of the methyl. So the name of this one would be sec-butyl methyl ether. Okay. And so this is the way we name really small ethers. An ether you should be able to recognize is one called tetrahydrofuran. It's abbreviated as THF. It's a really common solvent, and that's the shape that's shown there. Now, let's talk about naming more complex ethers. More complex ethers are going to be named using the IUPAC system, where one alkyl group is named as a hydrocarbon chain, and then the other is considered to be a substituent that's bonded to that chain. And so what do I mean by that? Well, let's say you have a really large ether here. So that's a really big parent hydrocarbon chain there. And when we look at this, right, we have a methyl group here. And so what we would call this then as a substituent name is methoxy as a substituent name. If we had two I got really wild with my drawing. Hold on. There we go. If we had two, right, and then a parent name, we would call that ethoxy, and we would treat it as a substituent. So name the simpler alkyl group as the alkoxy substituent by changing the YL ending of the alkyl group to oxy. So instead of this being methyl, it's oxy. And then name the remaining alkyl group as an alkane with the alkoxy group as a substituent bonded to this chain. So let's do an example. Let's come here and say we have this molecule, okay? We find the parent hydrocarbon chain. And we count, right? 1, 2, 3, 4, 5, 6, 7, 8. So that has 8. So that parent hydrocarbon chain is octane. And then we are going to treat this like a substituent. So we come here and we say, okay, great. We're going to count from the side closest to the substituent. 1, 2, 3, 4. And so then that would be 4-ethoxy. octane. Okay, so a longer chain, we're going to name those as substituents. Now, talk about how we name epoxides. There are 3 different ways to name epoxides. You can name them as epoxy alkanes, oxiranes, or alkene oxides. And so we're going to go through each one. So to name an epoxide as an epoxy alkane, you need to first name the alkane chain or ring where the O is attached, and then use the prefix epoxy to name the epoxide as the substituent. So let's talk about that. When we look at the ring, so let's say we've got this oxygen, and it forms a ring like this, but it's attached to a second ring. It's a really terrible ring. Let's pretend like it's a perfect hexane there, and let's count. So 1, 2, 3, 4, 5, 6. Okay, that's a cyclohexane. And so we're going to use that as the base name or the parent hydrocarbon chain. And then where we have this 2 connections here, we number it as 1 and 2, and now we name it as 1-2 epoxy cyclohexane. When we come over here, right? And for example, look at this. So we don't have a second ring anymore. What we would do is we would say, okay, hey, look, my longest parent hydrocarbon chain would be 1, 2, 3 right there. And we would make the 1 and the 2 as part of the ring. And so we would then name this as 1-2 epoxy 2 methyl propane. So you want to try to give the ring the lowest number. Now in both of these examples, the ring here has been at 1 and 2, and I want to show you an example where it wouldn't be at a 1 and 2, just so we can see lots of examples here. So let's do this one. Okay. When we look at this longest chain here, we have 5 carbons shown here. We would start numbering to give the epoxide chain here the smallest numbers from the right side, 1, 2, 3 right here. And we would call this 2, 3 epoxy pentane. Okay, so different ways to name these. The next kind of way we could name this is an oxirane. So epoxides bonded to a chain of carbon atoms, right, can be named as derivatives of oxirane, which is the simplest epoxide. So the simplest epoxide here is right here, and this has the common name oxirane. If we wanted to use this naming, for example, like this, the way this is numbered is the oxygen's at the 1, and then this one with the carbon next to the oxygen with the substituent is the 2, and then we have 3 here. So this would be, for example, 2,2-dimethyl oxirane, right? No number obviously is used for a substituent in a monosubstituted oxirane. So just a few things to kind of keep in mind. I find that most people tend to name those, tend not to use the oxirane names anymore, but I do like to cover it in case someone does. Now, epoxides can also be named as alkene oxides because they are prepared from alkenes, right? So for example, This is ethene, right? Which is also known as ethylene. And it goes through a preparation process where we end up with an epoxide, right? When this happens, to name an epoxide this way, you would replace the epoxide oxygen with a double bond and then name the alkene and then add the word oxide. So, for example, when we look at this would be like ethene oxide. Okay. Now, ethene shown here has a common name, ethylene, and so you will also see ethylene oxide. Personally, I find that using the first system to be the easiest, the epoxide system, just personally. But maybe you feel really strongly about another naming system, and that's okay. If I were to ask you to name an epoxide on an exam, you can use any of the 3 naming systems you like. But I do want you to be able to recognize any of the 3 naming systems and draw the structure from that. As always, if you have any questions, please feel free to stop by my office.